Something is stirring deep beneath China's Changbai Mountain, and it's no ordinary rumble. Scientists are detecting strange tremors, bizarre gas emissions, and a restless force unlike anything they've seen before. But this isn't just another volcano. It's a supervolcano, a sleeping giant capable of reshaping entire regions in a single, explosive moment. Hidden beneath its breathtaking crater lake lies a terrifying mystery. Why is this megavolcano behaving so differently? Could we be witnessing the first signs of an earth-shaking event? A force of unimaginable power is rising, and what's happening right now could change history. The awakening of the megavolcano beneath Mount Pictou, also known as Changbai Mountain in China, a disturbing phenomenon is unfolding. Seismic tremors are increasing in frequency and intensity, while strange gases are escaping from the ground. Deep underground, magma is on the move, signaling potential volcanic activity that could be far more catastrophic than a typical eruption. This is not just another restless volcano. It is a supervolcano, capable of releasing an explosion so powerful that it could disrupt global climate, devastate entire regions, and send shockwaves across the world. Scientists are racing against time to decipher the warning signs, but the situation remains unpredictable. What makes Mount Pictou particularly alarming is its history of extreme eruptions. Given its destructive past and the increasing seismic activity, experts warn that another large-scale eruption is not a matter of if, but when. Unlike most volcanoes that form along tectonic plate boundaries, Mount Pictou exists in an unexpected location, far from conventional fault lines. Traditionally, volcanic activity is driven by subduction zones, where oceanic plates sink beneath continents, creating magma chambers that fuel eruptions. However, seismic imaging of Mount Pictou has revealed a unique geological anomaly, a stagnant section of the Pacific plate trapped within the mantle transition zone. This subducted slab appears to be interacting with water-rich mantle material, creating conditions for magma formation despite the absence of an active plate boundary. This discovery challenges long-standing theories of volcanism and suggests that hidden forces beneath the Earth's surface may be driving activity at Mount Pictou. But before we can fully grasp the future threat Mount Pictou poses, we must first unravel the secrets of its explosive past, one of the most cataclysmic eruptions in human history. Mount Pictou, Changbai, the sleeping giant. Mount Pictou, also known as Changbai Mountain in China, is one of the most powerful and mysterious volcanoes on Earth. Straddling the border between China and North Korea, this massive stratovolcano has remained largely hidden from global attention due to its remote and politically sensitive location. At its summit lies a vast caldera, home to a crater lake spanning approximately 9.82 square kilometers, more than twice the size of Mount St. Helens crater lake. This enormous depression was formed during one of the most catastrophic volcanic eruptions in human history, forever altering the landscape. Despite its destructive potential, Mount Pictou has remained shrouded in mystery, largely unexplored for centuries due to its geographical and geopolitical challenges. The Millennium eruption of 946 CE was one of the largest volcanic explosions in the last 2,000 years, classified as a VEI 6 event. During this eruption, an estimated 45 to 100 cubic kilometers of volcanic material were ejected, and ash traveled over 1,000 kilometers, reaching central Japan and even Greenland. The explosion was so intense that it obliterated the volcano's upper half, creating the caldera seen today. This event had severe regional impacts, and if a similar eruption occurred in modern times, it could threaten millions of lives and disrupt economies across East Asia. Despite its staggering history, Mount Pictou has been relatively quiet for the past 1,000 years, but recent seismic activity suggests it may be waking up. What adds to Mount Pictou's mystery is its location itself. Geophysical imaging has proven it to be connected to the origin of magma at the site of an anomaly itself, an ancient portion of the Pacific plate that got entrapped into a mantle transition zone, just under the surface. This anomaly therefore identifies a different volcanism mechanism, not complying with classical plate tectonics theory, and adds a new dimension to the speck of knowledge we have about intraplate volcanism. Mount Peak-2 is currently one of the most threatening dormant volcanoes, and a resumption of activity could cause chaos in its wake. Between 2002 and 2005, increased fluctuations in seismicity were registered under the mountain, and unusual earthquake swarms were detected. The sudden escalation led to worldwide concern, prompting China and North Korea to collaborate with Western scientists and increase efforts to monitor the volcano as such. The danger is quite enormous, with over 1.5 million people living in the immediate vicinity of the volcano, and major metropolitan areas like Beijing, Seoul, Pyongyang, Tokyo, and Shanghai lay within the fallout zone for any volcanic eruption. Anyone who has experienced or studied the Millennium Eruption could ascertain that the eruption of Mount Peak-2 on an equivalent scale would wreak havoc across the world, especially with regard to the global climate and the destruction of a large portion of East Asia. Volcanic formation and plate tectonics. Most of Earth's volcanic activity is concentrated along tectonic plate boundaries, particularly in subduction zones where one plate is forced beneath another. These subduction-driven volcanoes form some of the most active and explosive volcanic regions on the planet, including the Pacific Ring of Fire, which stretches across Japan, Indonesia, the Philippines, and the west coast of North and South America. The key driver of this process is water, which is carried into the mantle by the subducting oceanic plate. As this water is released under extreme heat and pressure, it lowers the melting point of surrounding rock, generating magma that eventually rises to the surface in explosive eruptions. This process explains why regions like Japan, which sits at the convergence of multiple tectonic plates, are home to over 100 active volcanoes. Despite this well-established pattern, not all volcanoes conform to these tectonic rules. Some of the most famous volcanic systems, such as Hawaii, Yellowstone, and Mount Peak-2, Chongbai, exist far from tectonic plate boundaries, raising questions about their origins. In the 1960s, Canadian geologist John Tuzo Wilson proposed the mantle plume hypothesis, which suggested that some volcanoes are fueled by stationary columns of hot, rising mantle material. This model explained Hawaii's volcanic chain, where the Pacific Plate moves over a fixed mantle plume, creating a trail of volcanic islands over millions of years. Similarly, Yellowstone supervolcano in North America was linked to a deep mantle plume rather than traditional plate tectonic activity. Much like with the mantle plume model, Mount Peak-2 appears to contradict that, too. Seismic imaging has identified a unique anomaly beneath the volcano, a stagnant piece of the ancient Pacific Plate core in the mantle transition zone, lying below the surface. Unlike most subduction-related volcanoes, where slabs migrate deeper down into the lower mantle, this particular piece of the Pacific Plate appears to have stalled, bending horizontally instead of continuing its descent. This finding indicates a different volcanic mechanism, whereby the trapped slab interact with the surrounding mantle material, with the release of water and magma generation in an unusual location. Such behavior stands in stark contrast to volcanic activity associated with normal subduction processes or deep mantle plume mechanisms, flexing the limits of common geological understanding. The complexity of plate tectonics and intraplate volcanism remains an ongoing topic in science. The mantle transition zone beneath East Asia appears to host immense amounts of accumulated water, having built up over millions of years of subduction. Such water plays a crucial role in melting mantle rock and thereby sustaining volcanic activity far from conventional plate boundaries. Such anomalies have been noted in other volcanic fields throughout East Asia, suggesting that this particular volcanic process may indeed be much more extensive than previously envisioned. As signs of renewed seismic activity are evident around Mount Peak-2, the need to effectively comprehend such deep Earth processes has never been greater, not only for the sake of scientific enlightenment, but also for alerting these processes to potential future eruptions that may prove devastating. The mystery of Mount Peak-2's origin. Mount Peak-2's existence challenges traditional geological theories, as it is located far from any active tectonic plate boundary or known volcanic hotspot. Most volcanoes are found along subduction zones, mid-ocean ridges, or within hotspot tracts. Yet Mount Peak-2 defies these classifications. Its presence in an unexpected location, over 1,000 kilometers from the Japan Trench, puzzled scientists for decades. Unlike classic volcanic chains such as the Andes or the Aleutians, where subduction drives magma formation, there is no clear plate collision beneath Mount Pictou to explain its activity. This mystery has led researchers to investigate deeper into Earth's mantle, searching for an alternative explanation. A breakthrough came with seismic tomography, a technique that allows scientists to visualize the interior of the Earth using seismic waves from earthquakes. Studies in the late 1990s and early 2000s revealed a massive high-velocity anomaly beneath Mount Pictou, located at a depth of around 600 kilometers. This was surprising because typical mantle plumes extend all the way from the core mantle boundary at 2,900 kilometers, while subduction-related magma sources are usually much shallower. The seismic data showed that an ancient section of the Pacific Plate had become stuck in the mantle transition zone, rather than sinking further into the lower mantle as expected. This stagnant slab of oceanic crust appears to be a crucial factor in the volcano's activity. Further studies suggest an H2O-rich mantle transition zone beneath Northeast Asia, incorporating water that had been trapped in the subducted Pacific Plate over millions of years. Such a deep reservoir under immense pressure eventually leaks into the surrounding mantle, which lowers the melting point and produces magma. Mount Pictou differs from a standard hotspot, where heating results from core processes in an upwelling of magma. However, melting due to that hydration is probably the prime cause of its volcanism. This model accounts for the energy of one of the strongest volcanoes, particularly an energy source outside the realm of established processes, a long-term interaction of a water-rich mantle containing deep reservoir materials with a stalled Pacific Plate. The implications of this finding go beyond Mount Pictou. The presence of similar deep mantle anomalies underneath other intraplate volcanic regions in East Asia suggests that this process may be responsible for several isolated volcanic fields. The implication that stalled slabs in the mantle transition zone promote volcanic activity therefore contradicts the more traditional view that volcanism on Earth is strictly a phenomenon controlled by suture and deep mantle plumes. Once deemed unusual, Mount Pictou has begun to fit into a totally different category of volcanic manifestation, one which may help us further understand how the interior of the Earth influences phenomena occurring at the surface. As researchers pursue the anomalies of the system, they will glean important observations from the very origins of the volcano with respect to hidden forces at the behest of their shaping on Earth. Scientific investigations and breakthroughs. For much of the 20th century, Mount Pictou remained largely unexplored due to its remote location and geopolitical tensions between China and North Korea. A major turning point came when researchers used seismic tomography, a revolutionary technique similar to medical CT scans, to peer deep into the Earth. Unlike traditional subduction-driven volcanoes, this anomaly suggested that a stagnant slab of the Pacific Plate was trapped in the mantle transition zone, providing a previously unknown source of volcanic activity. Another prominent discovery establishes the role of water in fueling Mount Pictou's eruptions. Seismic imaging and geochemical studies established that the mantle transition zone beneath Northeast Asia contains vast amounts of water, taken in over the span of millions of years from the subducting Pacific Plate. Whenever this water gets released under increased heat and pressure, it lowers the melting point of the surrounding rock, which in this case generates magma at a depth that is not so common, many hundreds of kilometers away from an interface conventional for plate tectonics. This is in itself a huge challenge for existing geological paradigms, as it forwards a theory whereby deep mantle hydration could have major effects on volcanic activity in regions away from the usual subduction zones or mantle plumes. Along with this, the evidence also shows that Mount Pictou is not a unique case. Potentially similar processes are taking place in other intraplate volcanic fields in East Asia. Mount Pictou still remains a threat that is prone to unpredictability. Even the very secretive North Korean authorities allowed some Western scientists to work with them on the study of the volcano. Since then, international research teams have mapped the deep mantle under Mount Pictou, confirming that there exists a big low-velocity anomaly that shows the presence of molten rock just above the stagnant slab. These investigations continue to play a key role in predicting potential future eruptions and understanding the geological processes at a depth that operates on the structure of our Earth. But what if the very force that fuels Mount Peak-2's eruptions isn't just molten rock, but something far more unexpected, something hidden deep within the Earth for millions of years? The role of water in deep mantle processes. Water plays a crucial and often overlooked role in volcanic activity, particularly in subduction zones where oceanic plates sink beneath continental plates. As these plates descend into the mantle, they carry vast amounts of water trapped within hydrous minerals. Under extreme heat and pressure, this water is released, significantly lowering the melting point of the surrounding rock and generating magma. This process is the primary driver of volcanic activity in the Pacific Ring of Fire, where Japan, Indonesia, and the west coast of North and South America experience frequent and explosive eruptions. However, new research suggests that this water-driven melting process is not limited to active subduction zones. It also plays a role in fueling intraplate volcanoes like Mount Peak-2. Seismic tomography has revealed that a massive reservoir of water is trapped within the mantle transition zone beneath Northeast Asia. This zone, located between 410 kilometers and 660 kilometers beneath the Earth's surface, acts as a semi-permeable boundary where high pressures force water into dense mineral structures. The discovery of this hydrated mantle layer beneath Mount Peak-2 has reshaped our understanding of how water influences deep Earth processes. Scientists believe that over millions of years, water from subducted Pacific slabs accumulated within the transition zone, creating an environment where magma could form even in areas far from conventional tectonic boundaries. This revelation challenges the traditional assumption that volcanic activity must be directly linked to plate collisions or mantle plumes. Subduction of water-bearing materials has been invoked to explain the explosive eruptions of Mount Peak-2, apart in distance from the regular plate boundary setting of associated subduction, with the same inference allowing for similar locations of such large explosive eruptions elsewhere in East Asia. The long-distance influence into intraplate volcanic systems was considered toward deep water reservoirs, reputedly hydrogeological features yet painstakingly unrecognized in the context of intraplate volcanism. Wilson discussed how much water might control mantle melting at those depths, thereby providing insight into how some volcanoes form in unexpected places. This had far-reaching implications not only for Mount Peak-2 but also for some of the major volcanic episodes of Earth, involving large-scale flood basalt eruptions associated with mass extinctions and continental breakups. Large volcanic eruptions capable of as much alteration to the face of whole continents probably were fueled in a similar way by the rapid melting of a large volume of hydrated mantle material. Mount Peak-2's research has opened other discussions on the hydrology of geology through time and how this could affect volcanism, but also plate tectonics, seismicity, and the long-term evolution of Earth's atmosphere. Understanding this hidden role will help in forecasting any future eruptions, thus improving our modeling of Earth's deep interiors. The Big Mantle Wedge, a hidden volcanic engine. One of the most groundbreaking discoveries in modern geology is the existence of the Big Mantle Wedge, BMW, a massive reservoir of molten rock and hydrated mantle material hidden deep beneath Northeast Asia. Unlike traditional volcanic systems that are powered by subduction zones or mantle plumes, the BMW represents an entirely different mechanism of magma generation. Seismic tomography has revealed that a section of the Pacific Plate, which subducted millions of years ago, has stalled in the mantle transition zone. This stagnant slab has prevented normal convection, causing an accumulation of heat and volatile elements, including water, which triggers extensive melting in the mantle above it. This process has played a key role in shaping the region's volcanic activity, including the formation of Mount Peak-2, Changbai Mountain. What makes the Big Mantle Wedge particularly unique is how it disrupts conventional plate tectonic theory. Normally, when an oceanic plate subducts, it either continues sinking into the lower mantle or fuels surface volcanism along subduction zones, like those seen in Japan or Indonesia. However, in the case of the BMW, the Pacific Plate did not descend as expected. Instead, part of it became trapped and bent horizontally, forming a stagnant slab that stretches beneath a vast portion of East Asia. This geological anomaly has resulted in an enormous magma reservoir forming above the slab, one that is not connected to a subduction trench or typical mantle plume. The discovery of this feature has forced scientists to rethink how deep Earth processes can create volcanic activity far from plate boundaries. The BMW is one of the engines driving eruptions on Mount Peak 2. As the disparaged slab continues to exhale water-rich fluids into the surrounding mantle, it lowers the melting temperature of the rock material above it, producing a significant amount of magma. That is how, despite being more than 1,000 kilometers away from the Japan Trench, Mount Peak 2 is still an active volcano. In contrast to normal volcanic arcs, which are fed by direct subduction, this is totally dependent on the slow dehydration of ancient slab material. This piece of mature supersubduction Pacific plate, although subduction in this area stopped so long ago, has established a long-lived, hidden engine of volcanoes underneath, one that still keeps on providing eruptions. There could be several other stagnant slabs beneath other areas of intraplate volcanic fields in the West Pacific, which makes the understanding of isolated volcano formation incomplete. The Big Mantle Wedge presages volcanic activity all across East Asia beyond Mount Peak 2. The northern edge of the stagnant slab, termed the north-south gravity limit, acts as a boundary separating regions of major difference in crustal thickness, suggesting that it may have played a role in the development of other volcanic fields in China and Korea. Water-driven plume activity from the mantle transition zone raises the further prospect that among the most massive eruptions in Earth's history, huge flood basalt flows and supervolcanic eruptions might be attributed to these and neighboring deep mantle phenomena. The understanding that the volcano-energizing forces stretch far deeper downward than previously believed is now being validated by the continuing work of scientists studying the BMW, thus redefining the patterns of the interior of the Earth and its influence on the geology on the surface. Warning signs and monitoring efforts. In recent decades, scientists have detected alarming warning signs beneath Mount Peak 2, suggesting that the volcano may be reawakening. Seismic activity beneath the mountains surged dramatically, with a number of recorded earthquakes jumping from around 10 per month to over 200 per month. These deep tremors, occurring at depths of roughly 5 kilometers, 3 miles, indicated that magma movement was intensifying beneath the volcano. This sudden increase in activity raised fears that a new eruption could be on the horizon, prompting researchers to expand monitoring efforts and seek international collaboration to better understand the situation. One of the most critical tools in this effort has been seismic tomography, which allows scientists to create 3D images of the Earth's interior using earthquake waves. When researchers applied this technique to Mount Peak 2, they discovered a massive low-velocity anomaly beneath the volcano, a sign of molten rock accumulating in underground chambers. This discovery confirmed that the volcano remains volcanically active and is still connected to deep mantle processes. Additionally, seismic monitoring has revealed a large stagnant slab of the Pacific plate in the mantle transition zone, which plays a key role in fueling magma production beneath Mount Peak 2. These findings have reshaped our understanding of the unique volcanic mechanisms driving the region's activity. Even though it has a historically secretive policy, North Korea is going to unprecedented levels of international cooperation because of the growing concern about the eruption of Mount Peak 2. Aware of the risk, North Korean scientists teamed up with Western researchers to study the volcano's seismic activity. As such, many upgraded monitoring equipment have been installed, including GPS stations and advanced seismic sensors, for real-time observation of ground deformation and earthquake patterns. These instruments help detect possible early warning signs of rising magma, which could trigger warnings about an imminent eruption. However, some gaps in data still need to be filled because North Korea does not allow foreign researchers to assess its part in the reality of the volcano. The stakes of an eruption from Mount Peak 2 are exceedingly high. It could obliterate millions of people in the surrounding regions. The potential effect of an eruption similar to the Millennium eruption of 946 CE in both China and North Korea. The fallout would extend far beyond the immediate blast zone, potentially reaching major cities like Beijing, Seoul, Tokyo, and Shanghai, disrupting air travel, agriculture, and global supply chains. In understanding the warning signs, it is extremely important to sustain continued efforts in monitoring them, as it goes a very long way in alleviating devastation. Scientists have unraveled great strides in the mystery of Mount Pictou, and though its tomorrow is as unpredictable as any other, vigilance from both governments and researchers is what gives one a chance to prepare for the possibility of another catastrophic eruption. Potential consequences of an eruption. If Mount Pictou were to erupt on a scale similar to its catastrophic Millennium eruption of 946 CE, the consequences would be devastating. A modern-day eruption of this magnitude would be catastrophic, impacting millions of people across China, North Korea, and South Korea. The immediate effects would include violent pyroclastic flows, ashfall, and widespread destruction of infrastructure, making it one of the worst natural disasters in history. The sheer force of the explosion could obliterate entire communities, disrupt transportation networks, and displace millions of residents. Beyond the local devastation, a massive ash cloud could plunge the region into chaos. Volcanic ash can collapse buildings, contaminate water supplies, and destroy crops, leading to severe food shortages. If the eruption was strong enough to inject ash into the stratosphere, it could significantly disrupt global climate. A similar event today could have serious consequences for global food production, affecting not only China and Korea but also the broader agricultural markets in neighboring countries like Japan and Russia. From an international perspective, such ash cloud scenarios render some affected countries inaccessible by air for weeks to months, profoundly impacting air travel, trade, and supply chains. The cost of air traffic disruption amounts to billions of dollars, especially through the hazards of volcanic ash to aircraft engines. In tandem, major industrial centers may suffer aftershocks of power outages, contamination of electrically powered infrastructure, and even water supply destruction, thus prolonging already interested relief efforts. For people residing near the volcano, as well as almost 1 billion people under feasible fallout threat, the human welfare and economic cost will be inestimable. A major eruption of Mount Pictou would also bear serious geopolitical complications. Being perched along the borders of China and North Korea, any response to the disaster would require international cooperation. However, the response may be hampered by the isolationist policies and inadequate infrastructure of North Korea, thereby exposing millions to famine, disease, and displacement. Coordination of disaster relief and evacuation efforts, as well as airspace management, among the 3 states, China, South Korea, and Japan, would thereby place a heavy strain upon and bring to the fore regional diplomatic relations. Given the environmental degradation and economic havoc triggered by the eruption, such adversities could spark long-term geopolitical shifts in the region itself. Considering the risks posed, continued surveillance and scientific work, as well as emergency planning, remain paramount for lessening the anticipated impact of an eruption of Mount Pictou. The real question isn't if Mount Pictou will erupt again, but when, and whether we'll see it coming before it's too late. The future of Mount Pictou. Mount Pictou remains one of the most unpredictable and potentially catastrophic volcanoes in the world, and experts agree that another eruption is inevitable, though the exact timing remains uncertain. Earthquake swarms increased dramatically, suggesting that magma movement deep beneath the surface was intensifying. Though the unrest has since subsided, this does not mean the volcano is dormant, only that its underground processes are occurring on geological timescales, which can be difficult to monitor with short-term observations. Given its history of producing one of the most powerful eruptions in human history, Mount Pictou remains a serious concern for scientists and governments alike. One of the greatest challenges in predicting Mount Pictou's next eruption lies in its unique geological formation. This means that standard volcanic forecasting models may not fully apply, making it more difficult to anticipate exactly when or how an eruption might occur. Current research focuses on improving seismic monitoring techniques, analyzing gas emissions, and studying ground deformation to identify potential warning signs. However, with limited access to data from North Korea, scientists still face major obstacles in developing a comprehensive hazard assessment. Given the highly destructive potential of Mount Pictou, improving international cooperation and monitoring scientific efforts is imperative to prepare for future eruptions. In recent years, given both countries' increasing propensity to allow Western researchers to assist in monitoring activities in such a politically sensitive location, China and North Korea have made rare intrusions into cooperation territory. Notably, more real-time monitoring stations, satellite-based thermal imaging, and deeper seismic studies are needed to provide predictions. Also, it is time for the establishment of emergency response plans at the regional levels, especially in China, North Korea, and South Korea, where millions of people are located in the potential blast zone. Long-term activity at Mount Peak-2 remains unpredictable, but its geological context guarantees that it will erupt again, in the same manner that it last erupted in 1903. This could be a small-scale eruption, or it might erupt in a way that could be classified as a supervolcanic explosion, such as that observed during the Millennium eruption of 946 CE. Any large eruption today would inflict devastating damages affecting millions of people across Northeast Asia, disrupting economies and possibly impacting global climate. Scientists are studying the behavior of the volcano, but until better monitoring and predictive tools are available, Mount Peak-2 remains one of the most unpredictable volcanic threats in the world. One thing is clear: the next eruption is only a matter of time. Will we be ready when it happens? Let us know your thoughts in the comments below. If you enjoyed this video and want to stay updated on Earth's most extreme natural disasters, make sure to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. And don't stop here. Watch the next video on your screen for more fascinating insights into Earth's most dangerous and unpredictable forces. Thanks for watching, and we'll see you in the next one.